Good morning, everyone. Welcome to our Afterburner Nozzle detail design. It's good to meet all of you. I'm Casey Springer. We are Mjölnir Propulsion. I'd like to introduce my teammates, Ryan Tanner, Tim Carver, and Ben Wilson. Take you into an overview of our presentation today. We're going to give you some background about the project, some influence of how it came to be. We'll take you through our air source design, our custom air source, go right into the afterburner and nozzle, intricacies of the designs of both of those, our data acquisition system, how we tested, how we got our data, details about testing and the results we came up with, and we'll finish up with labor hours and budget and conclusions and some ongoing recommendations for the project. Right in project overview, last semester for preliminary design, we put together a low bypass turbofan engine for one of the AE teams for one of their propulsion systems. The engine created around 35,700 pounds of thrust. For the spring semester, we were tasked to design a scaled down version of one of the components of that engine. We chose to do the afterburner and nozzle sections, as these are the easiest to fabricate on a lower budget, on a lower scale. Pictured here is a completed picture of the rig we've created. It's got a custom air source that consists of a Chevrolet big block V8 engine, Garrett turbocharger. That combined air is passed into our afterburner and nozzle sections to create the mass flow that we require. Quick overview of the overall afterburner and nozzle design. This is a CAD image of the final product. Air flow is going from your right to left. It enters the diffuser section from the turbocharger, goes through the fuel rail inlet. The fuel air mixture is then slowed down in the afterburner duct and passes through the flame holder section, which creates swirl. It then passes by our igniter, which is a simple automotive spark plug. The fuel air mixture is then ignited and passed down the remainder of the combustion chamber in the afterburner and is accelerated at the nozzle throat. Designing this rig began back in December. We took some parameters from our low bypass turbofan engine and scaled it down based on the air source we chose. That was first in the making. The air source we designed as a custom setup in lieu of the air sources we have here on campus. We'll go into why that is here in a few slides. We went right into component sizing based on the mass flow we got from our air source, the calculated mass flow. From that, we went into the component design once we knew what size of burner duct and what size of nozzle throat we needed. From that, we went right into fabrication of components, and we did this with rapid speed. We knew that time was our enemy to begin with, so we went into testing as quickly as we could. Keep in mind, each subsystem of this rig was tested prior to a full system test. The engine and turbocharger systems were tested individually, as well as pieces of the afterburner, igniter, fuel system, with and without the nozzle, to make sure everything worked before a full system test. After testing was complete, we went right back into component design when we had iterations to do to increase the performance of the design. I'd like to introduce my teammate, Ryan Tanner.
Thank you, Casey. I'm going to be going over the air source design. So the air handling capabilities at Embry-Riddle. Right now we have a 500-gallon air tank. It's powered by a 25 horsepower compressor. There were concerns that using an air tank, as the tank empties, there would be a pressure and velocity drop. We were looking for something fairly steady. There's also fill time between runs, as well as mobility may be an issue trying to constantly connect to a large air source like this. There's a mobile electric blower. It's 7.4 horsepower. There's a lack of controllability on this. It seems to be, and then reliability issues with that have shown up lately. For comparison, the turbocharger output from the compressor is expected to be around 40 horsepower. So the first part of the air source is the engine. It's a 1970 Chevy 454. It runs off E85 ethanol and has 14.5 to 1 compression. It has a ton of power, plenty to spool up the compressor. The main reason we chose an engine like this was for fully controllable mass flow rate. We can adjust that just by regulating the RPM. We also used a Cessna prop controller so that when we got the RPM we wanted, where our mass flow was where we needed it, we could just be hands off and it would actually stay at that RPM. This gave us very consistent, reliable airflow where we could run for long periods of time. The turbocharger we chose was a Garrett GTP38R. It's a very common turbocharger. It's off Ford 7.3 turbo diesels. We have a lot of aftermarket, very easy to find parts. On the right is the compressor map for the turbocharger. The red dotted line was our corrected mass airflow from the 454 engine at 5,000 RPMs. We were expecting that we'd be somewhere along that line inside the compressor map while we were running this. However, we are running a decoupled turbocharger. What that means is that the air exiting the compressor is not running through the engine and then back into the turbo. So here's the air source. We have the engine, the exhaust spools up the turbo through the turbine and then exits to atmosphere. The turbine connects to the compressor with a shaft, which spools up as well and pulls clean air in and then sends that airflow back to the afterburner, or down to the afterburner. Once again, in a coupled turbo, the normal way turbos work, that compressed air would go back into the engine, through the exhaust, and then through the turbine. I'll now pass it off to Tim Carver.
Thank you, Ryan. I'll be discussing the layout and design of the afterburner. Some things to consider when designing an afterburner. First is that we wanted to facilitate combustion. This is going to add energy to the exhaust flow to give us the necessary pressure ratio required to achieve supersonic flow at the exit. Another constraint is the need to ensure combustion occurs at the appropriate location. That is to say, the afterburner is designed to withstand the combustion, whereas the turbocharger and nozzle are not. We wanted to minimize the total pressure loss across the afterburner. That's to help us with our pressure ratio at the nozzle and allow enough time to facilitate complete combustion of the air and fuel mixture. The first phase in the afterburner is the diffuser. The diffuser slows down the high velocity air coming off of the turbocharger to facilitate complete combustion. We elected to go with a dump diffuser as this is simple to manufacture. And things constraining the diffuser included the exit diameter of the turbocharger, the entrance diameter of the combustion section of the afterburner, and the conditions entering the afterburner from the exit of the turbocharger. The next phase in the afterburner is the fuel injection system. This introduces fuel into the air mixture. We're constrained by the want for stoichiometric combustion. Using 9-to-1 octane pump gas, this is going to require an air-fuel ratio of 14.7 to 1. We decided to go with fuel injectors from a 3.7 liter Chrysler engine. The decision to go with common automobile injectors was made so that we can have an injector that's already set up to handle hydrocarbon fuels. We ended up using 6 injectors controlled in pairs by switches on the control panel and pressurized with an aftermarket fuel pump. The flame holder creates a turbulent, low velocity area for combustion. We designed for simplicity. We like to go with a single V-gutter that runs the length of the diameter of the afterburner rather than using rings, as this is very, very simple to manufacture. Instead of optimizing a blockage ratio to minimize length, as length was not a concern in designing the afterburner, we picked a blockage ratio that would allow us to use a single V-gutter rather than a series of rings. After the flame holder is the igniter. This introduces the necessary heat to start combustion. We used a long thread automobile spark plug as our igniter as they're readily available. The voltage is provided by an ignition coil and controlled by a switch on the coil. The voltage to the spark plug is interrupted by an automobile relay, which allows us to have consistent spark throughout the duration of the test. Here's an image of our final afterburner. From the right to left is the diffuser next to the fuel rail. The flame holder and igniter are immediately after, and then lastly, the nozzle interface flange. I'll now pass it up to my teammate, Ben Wilson.
Thank you, Tim. I'll now be going into the nozzle design. So the purpose of the nozzle is to accelerate the exhaust flow, which adds kinetic energy to the exhaust. In preliminary design last semester, Mjölnir Propulsion designed a variable geometry convergent divergent nozzle, which is shown on the right. At its full expansion position, which corresponds to the afterburner in full operation, the convergent angle was 21 degrees, the divergent angle was 15 degrees, and the expansion ratio was 2.5. In detail design, Mjolnir Propulsion decided to design a static geometry nozzle rather than a variable geometry nozzle to simplify the manufacturing. We used the full afterburner convergent angle, divergent angle, and expansion ratio as shown above. The throat diameter was scaled down based on the available air supply of our air source. So in determining the nozzle throat diameter, the assumption was initially made that the entrance condition of the nozzle for the flow would be identical to the compressor exit conditions. This obviously doesn't account for the energy added by combustion. This was a conservative choice that was made to ensure that the flow would choke. Using these assumptions, the critical diameter was determined to be 1.34 inches, but the design diameter was actually even smaller at 1.25 inches. This extra conservative choice was based on the idea that if the throat was sized so small that it was adversely affecting upstream components, the engine could simply be throttled back. So it was important that the nozzle properly interfaced with the afterburner. The nozzle mounted on the afterburner duct with a flange and 4 bolts. There was also a sleeve that came off of the end of the afterburner duct that allowed it to fit nicely in the entrance of the nozzle. There was a gasket that was fit between the 2 flanges. This prevented leakage at this interface, and then also prevented dissimilar metal contact between the aluminum of the nozzle and the steel of the afterburner duct. So this is an image of the finished nozzle. And now I'll go into the data acquisition system. So the main objective of the data acquisition system was to measure the Mach number of the exhaust flow of the rig. This was done using a pedostatic tube that was positioned just after the nozzle exit. The total pressure and the static pressure that was measured through this pedostatic tube, they were used in the equation shown to determine the Mach number. Other measurements that were taken were more for a better understanding system behavior and for troubleshooting. Some of these measurements included the static pressure, and total temperature measured at the afterburner exit. And then we also recorded engine RPM from the ignition trigger signal of the engine. Shown in the image here is the electronics hub of the rig. There's a breadboard that contains some of the external circuitry, and then there are 2 data acquisition devices. The first data acquisition device was a National Instruments USB 6002 DAC. Coming into this DAC, we had 4 amplified pressure transducer signals. Going into the other DAC, which is a Digital Analog Discovery 2 DAC, we had an amplified thermocouple signal, and then we processed the 12-volt square wave ignition trigger signal that came from the engine's ignition box to determine the engine RPM as mentioned before. Both of the DACs output their data through USB, which was transferred to a laptop. On the laptop display prior to testing, this layout and input screen was what would be on display. It includes all of the input controls. The first thing that would be input would be the pressure transducer offsets. These are to tear the pressure transducers, bring them to 0 gauge pressure before the testing begins. The other inputs are more for internal calculations of the LabVIEW code. These include the afterburner duct diameter, specific heat ratio, and the atmospheric pressure. The atmospheric pressure would be measured externally using a smartphone app. During the actual testing, the output and controls VI would be on display. This shows all the system vital signs in a very intuitive and easy to read format so that any team member could tell at a glance what was going on with the system. The display is split into 2 major sections by the black bar in the middle. On the left side of the black bar, this data all corresponds to measurements that were taken upstream of the nozzle. Everything to the right side of the bar was data from downstream of the nozzle. Across the top, all of the graphs are live raw data coming in from the pressure transducers and the thermocouple. Going from left to right, it starts with the afterburner exit static pressure, then the afterburner exit total pressure, the afterburner exit total temperature, the nozzle exit static pressure, and then the nozzle exit total pressure. Across the bottom from left to right, there's a gauge for the engine RPM, the afterburner exit velocity. Down below, there's a small indicator for the afterburner exit air density. Then there's a gauge for the mass flow rate. On the far right, the large gauge is the Mach number of the exhaust flow with a supersonic indicator to the right that would light up red if our measurements indicated that we had supersonic exhaust velocities. In the middle, there's a write to file button that is used for writing a set number of data samples to an Excel spreadsheet when we decide to collect data. I'll now pass it on to my teammate Ryan Tanner.
Thank you, Ben. I'm going to be going over the testing. So our approach to testing was a crawl, walk, run approach. Basically, we began testing every component on its own as they were made. This gave us the ability to adjust the component if need be and understand how it worked on its own before putting them all together. This also helped with troubleshooting when we were doing the full system tests because we had a better idea of how each component acted on its own. Lab view and video data was collected at each test. The test site was in between the wind tunnel and axe fab. It is surrounded on 3 sides by concrete walls. It's very easy to cordon off, and it's away from foot traffic. This was approved by safety. Every test had the same setup. Every member had their same role for each test. Starting at the top going counterclockwise, Ben was doing data collection. Casey was at the front of the rig controlling everything. I was to the right of the rig doing temperature sensing, watching all the components, making sure they were at a safe temperature. Tim was on the right as well, doing visual inspection and making sure there were no leaks. There are 2 fire extinguishers, 1 on either side. We had 3 blast shields, 1 on either side of the afterburner at 45 degrees and 1 directly in front of the control panel. And we also had a battery disconnect that we could easily get to if there was reason or need to shut the entire thing down quickly. Subsystem testing began on February 16th. First was just an engine control system check. This was where we ran the engine to get used to the controls and kind of get a feel for how it was going to perform with the controls we had. The next was a full air source. The point to this test was to spool the turbocharger and make sure we were not over spooling, get an idea of how the turbocharger was going to react to being uncoupled. From this test, we actually noticed a little bit of leakage and ended up rebuilding the turbo just to ensure the integrity of it. We also did a spark test to ensure that it would remain on when we flipped the switch. The fuel system test consisted of first pressurizing and watching for leaks and making sure everything was deadheading like it should. And then the second part was to flip the injectors open and watch how they atomized. Then the last subsystem was the afterburner nozzle. From this one, no spark or fuel, just running the air through it, all of it together to kind of understand the vibrations and how everything was going to work together, and also to begin initial electronics testing. This video is of the fuel injector test. You're looking inside of the afterburner. The cylindrical flame holder is in the center there, and you'll see the fuel coming from behind. And that was at 1/8 speed. For full system testing, we began on April 3rd. The first one was a flame and ignition test. This was to look for repeatable behavior as well as try to understand at what RPMs the system would light and how it would react to different RPMs and different lighting conditions, such as more injectors or less injectors. A lot of the observations we noticed at this time, there was popping, unstable combustion, and a lot of pressure that would basically backfire out of the compressor. We were also getting very hard starts, and we felt that we needed better ignition and swirl inside of the afterburner. From these tests, we determined some design iterations that we needed. The first was a flame holder. We switched from a cylindrical flame holder to the V-gutter. This gave us longer stay time and a better combustion time inside of the afterburner. We also created a swirler check valve. This was placed in between the compressor and the afterburner. The idea was that the compressed air coming in would get a better swirl, and therefore it would help to atomize the fuel as it went through, as well as when we got the pressure bursts heading backwards, this would close and keep it from heading through the compressor and stalling it. We also adjusted the spark plug location. We set it down deeper into the afterburner for easier ignition. After we did the iterations, we found we were getting much more stable flames. We were able to actually get some decent testing, so we began performance tests on April 15th. This was to measure and record the performance of the afterburner and collect data to evaluate the design. I'll now pass it out to Team Carver for the final results.
Thank you, Ryan. Here we have a test video of one of those iterations we conducted. At the end of the video, there will be a couple points I'll point out to you. A couple things to point out. First, you might notice the general toothiness of our graphs. We attribute this to the rumble and roar, the shake of the whole test rig, which really amplified the connectivity issues we were having in our breadboard and transducers. Second, how clean the flame looked. We were able to get that sort of repeatability and consistency throughout the duration of our performance test. From the test results, we were able to collect some data. Most notably, the engine RPM, we kept it consistently right around 3,200. The exit static pressure of the afterburner at 13.3 psia, and the total temperature at the same location of 2,390 degrees Rankine. This corresponded to a mass flow rate of 1.22 pounds per second, which all sum together an exhaust Mach number of 0.37. Here's the compressor map shown again with our data laid on top of it. We can point out that our data does not fall inside the compressor map, which is the reason we think that we weren't able to get the supersonic exhaust flow, or excuse me, the supersonic velocities at the exit of the nozzle. We attribute this to the nature of the turbocharger being uncoupled from the engine, as that's not something we're used to dealing with, and there isn't a whole lot of data out there on it for our research. I'll pass it back to my teammate, Casey Springer.
Thanks, Tim. We'll be going over the labor hours and budget for this project. Start with labor hours. The graph shown here depicts our target number of hours as opposed to our actual hours worked. The predicted number of hours comes from the idea that you spend 2 hours outside of class for every scheduled hour inside of class. This comes to around 617 hours. Actual hours worked as of last night around 9 o'clock comes to 1,634 hours. Between the four of us. This project is very hands-on, more so than other detailed projects. Most of the time during class time we came in, checked in, and went right to the shop to go back to work. Many iterations had to come with the project, as well as construction of the entire rig, which began in December. This is a cost breakdown of what hourly rates for each category would be, developed into 5 categories. Over 57%, or approximately 57% of the hours worked are technical hands-on hours. The overall budget given to us by the College of Engineering was $1,000 beginning in January. Our estimated value for borrowed and donated parts for this rig is over $12,000, engine being the biggest money pit. The turbocharger, fuel pump, and the oil pump for the turbocharger were all borrowed parts. The rest of the budget was used for the nozzle aluminum stock we purchased, as well as afterburner instrumentation fittings. The pitot tube was also purchased, and electronic wire, two-way switches, small items were purchased with the budget. In the end, we came out to around $775 spent on the rig we purchased through the College of Engineering. Into conclusions and recommendations on the project. As an overall conclusion, we had 4 major goals at the beginning of the year. First was to build a mobile air source to feed our afterburner nozzle. We have successfully created this. This is a one-off air source that has not been created before, and it has been successful in its creation. Also, the fact that we have built a functioning afterburner is significant. It does raise our pressure, it does raise the temperature, and it does accelerate the fuel, the flow coming out of the nozzle. Not quite to what we expected or wanted, however, we do see data that proves it. Also, that going into collecting data from our afterburner testing, we have successfully done that as well. The only objective that we did not meet during this project was to observe supersonic exhaust flow and to measure it due to our pressure rise. We came in shy of our pressure rise, and therefore we were below choke flow at the nozzle throat. Going further in this project, there are a handful of iterations we would do had we had the time and money. First being a smaller afterburner duct, we would decrease the diameter of the combustion chamber. To give you an idea, the Ford 7.3 liter power stroke is approximately 444 cubic inch motor. That's what this turbo was designed to fill. This afterburner duct we've created is 26 inches long, 5-inch diameter. It comes out to about 511 cubic inches. And that's based on the idea that turbocharger feeds around 2 cylinders at a time. So we have concluded that this is one of our biggest flaws, is that the turbocharger is not a big enough turbocharger to sufficiently fill the area we've created for it. Also, another design iteration that we would try is to utilize a supercharger for the airflow. This idea was brought up in January. We actually contacted Vortec Engineering out of California and asked them if they would be interested in a sponsorship for a centrifugal supercharger. However, they ended up not being interested after a week on the phone. This is something we would pursue if we had the time. The other change would be to change the breadboard we were using and go to a printed circuit board. This would eliminate a lot of the noise we had in our data, as well as fix any of the loose wire connections we experienced. This was all during testing. We fought with instrumentation, and this was a big part of it. The last thing we would change, we would install a load device on the engine for optimum performance. This is another factor that affected the performance. The engine is running unloaded currently. There's no load on the flywheel. If we installed some sort of load device, whether that be a transmission, hydraulic pump, some sort of power takeoff, that increases your cylinder pressures, gives you more flow and more energy out of the exhaust to spin the turbocharger. Recommendations for other teams. What we did, we designed for what was available and not necessarily what was desired. We were warned early on that time was definitely our enemy and that we needed a product put together. Most of this rig was put together from scrap pieces in the back of our machine shop, as well as borrowed pieces from the propulsion lab. We spent very little time having to wait on intricate parts that were purchased. We allowed for complexity rather than complication. What I mean by that, the rig in itself, it is a complex machine made of very simple parts. No parts in this rig, even the intricate ones that were machined, are very complicated at all. It's a very straightforward process where we machined it and we put it together. Being proactive in this project is how we got this far. We came off with a CAD model of a low bypass turbofan in December, and with an idea of what we wanted to do for spring. Over Christmas break, we assembled the engine stand, just a basic stand, and about half of the control pedestal, and got it here to work on this, this semester. Again, we knew time was our enemy, and we were warned about that multiple times. Afterburner projects in the past have failed because of this. We expected iterations to happen from the get-go. Nothing works the first time you put it together and try it out. This was a big learning curve for us. We allowed for time to do iterations and fix the problems we observed. This was another reason for all the subsystem testing that began back in February. Another recommendation that helped us out a lot is get to know our shop technicians. That was a big help. We spent almost every day in the shop Most of it was 7 to 8 hours a day working around these technicians. It helped us out quite a bit to get to know them and become friends with them. Team dynamics is a major player in a project, especially like this one. We spent 30 to 40 hours a week with each other. We need to know how to get along. Biggest takeaway from this project, as far as team dynamics goes, is to have a common goal. All of us knew what we wanted out of this project and how to go about it, and we all agreed that we were going to work together to do it. Trusting each other goes into trusting each other. You trust each other in each other's work you do. We did not stay necessarily in our own lanes on this project. We all had a specialty of this project, but we went behind each other, helped each other, and we all had a hand in everything on this rig. Being confident, not cocky. This is sort of a term we kind of adopted back in our test readiness review. We're confident in our work and our material and the way we run and test the rig and the way we make iterations. As soon as you get cocky and complacent, you miss steps and you end up failing. And also to remember to celebrate success. Take pride in your work and you produce something great. I want to throw out a special thanks to those listed above, the big ones being Dr. Mike Fabian, Brenda Haven. They helped us out along in the project every step of the way. Big influence on all of us. The guys in the shop, Ernie, Jeff, and Patrick, it wouldn't have been possible without them. Again, we got to know those guys along the way, and we're all been great friends. Matt Springer for donating the engine, also Lead Auto Service in Colorado Springs for donating the turbocharger. Dan Danley and Dr. Elliot Briner, they helped us out with instrumentation issues along the way, which did plague us. And Ryan and Aaron, they helped us out with photography and the logo as well. I'd like to open the floor for any questions.
Really good job. That's a lot of work for 4 people. It's a lot of work for more than 4 people. So I commend you for the progress that you've made. Now, when you translated your design, your Afterburner design, the expectation was you're going to try and match or scale the properties to match your air handler. That's huge. That's a huge thing. So what were the challenges that you had? What do you think you got right, and what do you think you got wrong in that process?
I think the big thing we got right, we used the same entrance and exit angles of the nozzle, based on the fact that we used a compressor map to map out what the turbocharger, what we thought it was going to produce as far as the pressure ratio goes. That was an experimental part of it, being that it's an uncoupled system for the turbocharger. It didn't react like we did, like we expected it to. We sized it based on our mass flow coming out of that. We found that that was inaccurate, the way we assumed it was going to behave.
Okay, so a little bit into the project, when you were realizing that you weren't getting the total pressure that you were hoping to get, did you do a total pressure loss analysis? You have a dump diffuser in there. Do you have some idea of what the flame holder and the dump diffuser and the length of your afterburner? Any idea on how much total pressure loss that was going to kind of eat up by the time we got to the nozzle throat?
No calculations going on it. We know that the design of the V-gutter in the end, we knew we wanted to minimize our pressure loss against it. And we know from before that afterburners of this size, they've always had a blockage problem and that's too much pressure loss, which is why we opted for a single flame holder. That was to the extent of the design of that.
Yeah, thank you.
So you probably said it, but I think I missed it. Well, first of all, creating an afterburner out of a 454 is stinking cool. And that whole rig is awesome. But the piece that I think that I missed was, the end goal of this was that engine. And it felt like the only thing that really got designed was the nozzle in terms of scaling it to the engine. And the afterburner, I felt like that was just a tube that you put the V-gutter thing in there. That's not really how the engine would be. And so how do you take your cool test rig and scale that up to the engine that you actually were supposed to be designing for?
Well, it would kind of be the opposite. What we took out of our engine design originally was the nozzle dimensions. And based on that, we took our flow coming off of a scaled down air source, and then we created basically the combustion chamber out of that. So it'd be sort of the opposite. Answers your question.
Yeah, I guess I'm not.
They have to build and test hardware, and you can't build a full-up afterburner
Yeah.
nozzle until that's over $1 million, and they have 1,000.
Yeah. Okay, so speaking of which, go to your labor hours chart.
Come on.
That one. So, believe it or not, our managers look at charts like this every week. They really do. And they got the projected thing there. And if you start getting a slope like that, they're going to freak out. And yeah, it's cool, you guys did it, you put in a lot of hours. But when you're out there working on a government contract, this is gonna be a showstopper. It will be, this is not a comment on your work. I just wanted to point this out, that when you get out there and you start seeing something like that, now you gotta go to the government and ask for more money. It's bad. And the funny thing is you'll get in just as much trouble for being below the line. They want you right on that line. And so when you're developing contracts and working on a contract, they look at this stuff. You guys probably thought this was sort of an after thing. Managers look at this all the time.
If I could comment on that.
Go ahead.
Real quick. Me and Dr. Fabian had that exact conversation. We understand that when you quote a job or any kind of contract, that's a big no-no. That was not a constraining factor here. Back in January, we were told we had a product to build, go build it. So.
Yeah, and it becomes hard. It's like, I don't know how we're gonna get this done in the hours that we projected, and then you gotta go back to the government.
Sure.
Yeah, I want to say overall, really good job, really well polished presentation. It was really awesome to see. Yeah, cool project to do. Only real question is, did you have any idea how to solve your noise problem that you had with the data, or do you think it's just purely from the vibrations and stuff like that?
What do you mean by noise is mostly the total voltage drops. It would drop absolute zero signal. Those were really easy to distinguish looking back at the data later. To fix that, yeah, we definitely go with a printed circuit board in the future. Since it was on a breadboard, there was connectivity issues. The system started vibrating, you get random voltage drops. So making those actual hard connections in the future would be ideal. Some of the noise in the pressure, some of that's attributed to the dynamic range of the pressure transducers. They were actually 100 PSI pressure transducers. We were looking to measure within 30 PSI, 0 to 30 PSI.
Yeah, that makes sense. No worries. I was just kind of curious if you guys had thought about that at all. But I think that you guys had hit on something really cool that no one else really talked about, like your team dynamic stuff. And the thing that really stuck out to me was the be confident, not cocky thing, because I've only been in the workforce for a couple of years, but that's what makes the difference between especially young engineers, the good ones and the bad ones, is the ones that are confident, but they're not cocky. And that's huge. So, because I work with some people that are very cocky, they're not doing that well. So that's a big takeaway, and I think that's a really good lesson that at least you had it here too, for sure, and then take that with you into industry for sure. Yeah, good job, guys.
Great job under incredible constraints. I have a couple of points of personal curiosity. Choice of aluminum for the nozzle. Did you give any thought to the maximum duration of a run that you could do before that aluminum started getting soft?
Yes, we did. We looked at temperatures of combustion and things like that, just to see what temperatures we could expect in there. And then we looked at the melting temperature of aluminum, and I don't remember them off the top of my head, but it was a safe range. I don't know how long we could go before it would start affecting it, just because of long-term heat transfer, but the temperatures themselves were within safe ranges.
Why gasoline instead of jet fuel?
It was readily available.
Okay, if I were doing it, I would have been afraid to use gasoline, so I would have trucked in some jet fuel, but that's just me. Last thing is you got tremendous shaft horsepower on that 454, so maybe this was your supercharger recommendation, maybe for another team in the future to utilize some of that shaft horsepower to turn something else to produce, I think, more and higher pressure air source. I think that would be an interesting follow-on for another team. Because like you said, you were running it unloaded. They don't really like to do that, and it seemed like you just weren't getting enough airflow through there.
Oh, we're proud of our testing dates because I pulled the valve cover off yesterday and I have a problem on the number 4 intake rocker. So.
Do you attribute that to running unloaded?
Yes.
Yeah, okay.
That was from the beginning. We looked into finding a hydraulic pump and tying the lines together.
Mhm.
And I just put a load on it. Didn't have money for that either. So they wouldn't give one to me.
Yeah, fantastic job given the constraints. Thanks.
All right, thanks very much, guys. Good job.